Okay, this is section 5.4. We're talking about exponential functions. We'll start with the warm-up, but I want to do something before I start with the warm-up. Exponential functions. Hold on a second now. Okay, so the question is, how do exponential functions work? And the answer is just like linear functions, except multiplication or division instead of addition or subtraction. So I want to give you an example of that. So we'll start with a linear function. We write that as f of x equals mx plus b. And over here, let's have an exponential function. G of x equals c times a to the x. So notice in both cases, you have an x, and you have two letters. You have an m here, which is our slope. I'm going to call it a linear slope. Then we have an a here, which is our base. And I'm going to call it our exponential rate of change. Another word for slope is rate of change. So linear rate of change is slope. And then you have a b here, and we know that's our y-intercept. And you have a c here, and that is our y-intercept. Okay, so let's start with linear functions. Think back to when you were first learning your arithmetic, and you learned addition first, and then subtraction, and after that you learned multiplication and division. Addition and subtraction belong over here in our linear world, multiplication and division belong in our exponential world. In a linear function f of x, for every 1 unit increase in x, I add the slope m to the output. So as an example, if f of x equals 3x plus 2, when I have x equals 0, I have 2. If I increase x by 1, I have 2 plus 3, which is 5. If I increase x again, I have 2 plus 3 plus 3, which equals 8. I'm adding that slope every time. For an exponential function, g of x, for every 1 unit increase in x, I multiply the output by the exponential rate of change. So instead of adding the linear rate of change, which is m to the output, I multiply the exponential rate of change to the output. So if g of x, I'm going to use the same numbers for a very particular reason, is 2 times 3 to the x, then when x equals 0, g of x is 2 times 3 to the 0, that's 2. If x equals 1, I have 2 times 3, which is 6. If x equals 2, I have 2 times 3 times 3, that's 9, times 2 is 18. So here I'm adding n each time. Here I'm multiplying by a each time. So whenever you are working with exponential functions, think of them as similar to linear functions, except you multiply or divide instead of add or subtract. And we'll do and when we go through the warm-up, or similar examples to the warm-up, we'll see an example of subtraction versus division. All right, moving on. So here's a warm-up question 1 or something similar. Warm-up 5.4, similar to 1. Let's make a table. Here's X, here's Y. I ran out of room, so I'll write it here. Let's say it's 5 times 2 to the X. You might see this written as 5 times 2 to the X. I prefer the multiplication because that's easier for me to say this is the 2 to the X and that's the 5. So we'll come back to X equals minus 2 and X equals 1, but let's just start with 0. Okay, when X is 0, 2 to 0 is 1. So Y is 5. That's why this right here is our y-intercept. Now if I increase my input by 1, I multiply 5 times 2 equals 10. And multiply by that exponential rate of change. If X is 2, I can do the math where I can say multiply this output by 2, which is 10 times 2, which is 20. If X is 3, that's 20 times 2, which is 40. And if X is 4, that's 40 times 2, which is 80. Every time you increase X by 1, I multiply the output by the exponential rate of change. Going the other way, when you wander in the negatives, you just divide the output by the exponential rate of change. So if I go from 0 and go back by 1, I'm going to divide the previous output by 2. And if I go back by 1 again, I'm going to divide that previous output by 2 again, and I get 5 over 4. Just like in a linear function, if you go to the right, you're adding the slope each time, and if you go to the left, you're subtracting the slope each time. With an exponential function, when you go to the right, you're multiplying the output by the exponential rate of change each time, and when you go to the left, you're dividing the output by the exponential rate of change each time. So that basically covers question 1. Let's look at the next one. We need maybe a little more space here. I've got X, I have some unknown function g of X, and I want to find the formula for g of X. So if I'm told that it's exponential, I can write down the general exponential form. I like to use C and A. The worksheet used A and B, so don't get that confused. The exponential rate of change is the base, that's where the power of X goes. And the coefficient, which is why I use C, is also the y-intercept. So now I have some information. I know if X is -1, g over X is 1/8. If X is 0, g over X is 1/2. I move up. And if I want to know what C is, I'm just looking for the y-intercept, because when X is 0, that term goes away. That's right here, so C equals 1/2. And if I want to know what A is, I ask what happens to my output every time I increase the X by 1. 1/2 to 2, that goes up by 4. That's a little confusing, just go from 1 to 2. It goes from 2 to 8, that's multiplying it by 4. So that must be every time X increases by 1, my output is multiplied by 4. All right, let's do one with exponential. So these are both examples of exponential growth. Just because as X increases, Y grows. As X increases, Y grows. But we can also do exponential decay. Which is every time X goes up by 1, the output is multiplied by a fraction constant fraction that is less than 1. So I'll do 2 quick examples. The first is just a table. So if I have x here, and if I have g of x and I don't know the formula, if I come up with that, I usually just start right at the y-intercept. So if you see a 0, 3, that means the y-intercept is 3. That means that coefficient is going to be a 3. And we need to fill in that number. So if x goes up by 1, and this goes down to, let's see, how about 3/5? If x goes up by 2, or from 1 to 2, and this is 3/25. If x goes up by another 1, and that's 3/125, and you can see these numbers are getting smaller and smaller and smaller as I increase. Here's 3, here's 3/5, here's 3/25, here's 3/125, and it's quickly coming down towards 0. I'll do one more. And if I go the other way, well, if this goes from 3 to 3/5, so that's being divided by 5. So this needs to be multiplied by 5. So it should be 15. So over here at -1, it should come all the way up to 15. So one common mistake is to look at when x equals 1 and think that is my base, but that's not my base. The base is not the y value corresponding to x equals 1. The base is the multiplying factor that goes from 0 to 1, goes from 1 to 2. So 3 going to 3/5 is multiplied by 1/5. And that's a good time to use parentheses, so you know you're raising that whole 1/5 to the x. And so the base is not whatever matches with 1. It's whatever the change is from 0 to 1, or the change is from 1 to 2, whatever that multiplication change is. All right, I said I'd do 2 quick examples. I'm just going to do 1 example, and then we'll move on. Let's start looking at, we'll go through a summary really quickly. This is page 134. All right, I'm going to use the same notation, even though it's not what I normally use. Y equals b of x, or y equals a times b of x. A is the y-intercept. B is the base, which is the exponential rate of change. Okay, the y-intercept, we can also call that the coefficient. And the exponential rate of change tells you every time x goes up by 1, the output is multiplied by b. And that's about all you need to know for our summary. But I'm going to add one more piece of information. If b is greater than 1, we have growth. And if b is between 0 and 1, we have decay. And those are the only values we allow for b. B cannot be 0, it cannot be negative. And if b equals 1, it's just really boring, because 1 raised to any power is just 1. So if b is greater than 1, you're multiplying by a growth factor. If b is between 0 and 1, you're multiplying by a decay factor. But the process works the same. So let's do an example. I've given a little bit of information here. I know this is the point 0, 7, and this is the point do 2, 7/9. And I want Well, first of all, I look at this function, I say that looks like my parent function, exponential. It's going down, but it does look like an exponential function. So I'm gonna write it as a general exponential function. I'm gonna fill in some information. The first piece of information I can fill in is the coefficient, because that's always the y value of the y-intercept. So g of x, that leading coefficient has to be 7. And now I'm saying, okay, as I go from x equals 0 to x equals 1 to x equals 2, my output goes from 7 to 7 times 1/9, but that's for x equals 2 steps. So if x equals 1 step, well, if x equals 2 steps, I end up multiplying by 1/9. That means x equals 1 step maybe goes from 7 to 7 times a third, and I can check that, because now I go one more step and I multiply a third again and I get a 9. That makes sense to me. I go from 0 to 2 and I multiply by a third 2 times. So if I go from 0 to 1, I'm going to multiply by a third 1 time. And that product right there, or that factor right there, that is my base. That's my exponential rate of change, which in this case is going to be decay, because as x gets bigger, my y values get smaller. That was, sorry, I should have started this. This is like question 1 on page 134, an example 34. All right, moving on. That graph is helpful, but I don't really need a graph. All I need is 2 pieces of information. And pause it and come up with some points. So suppose I have an exponential function of the form g of x equals c times a to the x, and the points 2, 192 and 3, 8,736 are on the curve, are on the graph. So I have 2 points, I'm missing 2 pieces of information, so that's going to be enough for me to figure this out. So let me just make a table to start. That's going to help me. And I have x, y, 2, 192, 3, 8,736. Now, if this were a linear equation, to get the slope, you would look at subtracting y1 and y2. But we don't do that here. Here we look at dividing y1 and y2 to get the exponential rate of change. So as x goes up by 1, y goes up from 192 to 8,736, and it can be really helpful to actually write this sentence down. And when we do that, another way I could say that is 192 times my exponential rate of change should equal 8,736. And this is the key. If y goes up from 192 to 876 by multiplication, it's multiplied by my base. So 192 times the base should be 8,736. And so if I divide both sides by 192, I get that a equals 8. So now I found my exponential rate of change. So g of x equals some c value times 8 to the x. And to find my c value, I need to just work backwards until I get to 0. Well, let me just do that. Extend my table a little bit. I'll start over just because it can be helpful to start over. But you could just stick a 2 down here or something. Okay, so this way it divides by 8, right? Because this way it multiplies by 8. So as I go to 1, I'm going to divide by 8 again. So we ask, what is 192 divided by 8? 192 divided by 8, that's why we have calculators, is 24. And if I go back one more time, what's 24 divided by 8? It's 3. And now I found my y-intercept, which is my coefficient. We might need to watch this a couple times to see the logic behind what I did. First, I wrote the points down, then I wrote it as a sentence. As x goes up by 1, y goes up from 192 to 8736 by multiplication, which helps me write an equation with a that I can then solve for a. Then I just extended my table, and I thought if x goes up and I multiply, then when x goes down by 1, I divide by 8. I just divided my way all the way back until x was 0 and I got 3. All right, moving on. I basically covered the summary box, and I'll go over that in class as well. I'll fill that out completely. So now we have an application. Invest $2,000 in a business where the return, or how about the future value, can be modeled as 2,000 times 0.87 to the t, where t is years. Okay. So the initial value that's invested is that y-intercept. Initial investment is 2,000. Is it growth or decay? Do that, you say every time t goes up, my initial investment is multiplied by a number less than 1. That means it's going down, so this is decay. And how much does it decrease by every year? Here's a very common mistake. This is not how much it decreases by every year. Not the decrease. This is what is left. So my first year, I end up with 87% of what I had left. So the percent decrease is 100 minus 87%, or 13%. Now, if you're thinking about investing in something, life is tough if you're losing 13% a year. But life is ridiculous if you're losing 87% every year. So that can kind of give you a clue. It wouldn't make sense to do a financial problem where you lose nearly all of your investment in the first year. All right, and then what's the value at t equals 3 years? I'm not going to write out everything, but the value is 2,000 times 0.87 cubed, whatever that number is. And you just plug in and go. Okay. Another question you might be looking at is finding as a growth or decay. Growth or decay. So if I tell you I have a function uh, 20 times 0.91 to the minus 0.4 to the x, the base is this. All right, that's the exponential rate of change. There's a couple different ways to figure this out. First way, simplify the base. .91 to the minus 0.4 is the same as 1 over 0.91 to the fourth, which if we do that is 1.038. This is bigger than 1, so that's growth. That's a fraction, might make you think decay, that's a minus, might make you think decay, that's a decimal, might make you think decay. Just simplify the base, grab your calculator, multiply it out and see what that number looks like on a number line. And if that number is bigger than 1, it's growth. That's the first way. The second way, I think, is easier. Test x equals 0, test x equals 1. X equals 0 is easy. F of 0 is 20, because that's what we get right there. And as long as I'm careful with my parentheses, f of 1 is 20 times 0.91 to the minus 0.4 raised to the 1, which is 20 times 1.038, which is approximately 20.8. That grew, so it's growth. So you can actually find out what that base is in simplified form, or you can just test to see if your function grows when x increases. If your function gets smaller, if it decays, then it's decay. That's how I would approach those type of questions. And then there's some tables to try and figure that out. I think you're good with that. Yeah, I do want to sum up though, because this is super important, especially when we get to logs. Linear is addition or subtraction. Exponential is multiplication or division. And if you understand this relationship, you can use all your tools from linear functions, which most of you are very comfortable with, to investigate exponential functions. You can solve exponential equations pretty easily. If you remember, your tools are similar except for multiplication, division, except for addition and subtraction. And you can understand how graphs work. You can set up and interpret questions. As long as you understand addition in linear is multiplication and exponential, subtraction in linear is division and exponential.